All right, it's
Yeah.
JM and Andrew, and we are barricaded in the library because there's about 100 million people trying to do their projects.
At the
So,
same time.
yeah, it's pretty awesome. So, anyway, our project we're doing is linear programming, which is we found out to be tons of fun, and also that no one else in our math class knew anything about linear programming. So, what linear programming is a type of optimization used to find the maximum or minimum of a quantity. In a two-dimension linear programming problem consists of a linear objective function and a system of linear inequalities called constraints, which you will see us do in detail. We'll give you examples of stuff, and JM's going to do stuff too. And okay, so let's get started. Our first problem is kind of long, the way you can see.
Kind of long.
But we did this one and the next one to help explain linear programming because they really went in detail with the steps. So here's problem one. A publisher has orders for 600 copies of a certain text from San Francisco and 400 copies from Sacramento. The company has 700 copies in a warehouse in Lodi. It costs $5 to ship a text from Novato to San Francisco, but it costs $10 to ship it to Sacramento. It costs $15 to ship text from Lodi to San Francisco, but it costs $4 to ship it from Lodi to Sacramento. How many copies should the company ship from each warehouse to San Francisco and Sacramento to fill the orders at the least cost? And this is actually one of the hardest parts of a linear programming problem is understanding and sometimes reading the word problem itself, because you got to take the word problem and get your constraints and unknowns from there, which we have right here. Here, so JM.
So we have to find the unknowns first, and we'll have x equaling the number of books from Novato to San Francisco. Y is the number of books from Novato to Sacramento. Z is going to equal the number of books from Lodi to San Francisco, and W the number of books from Lodi to Sacramento. Well, first we have to minimize the cost. We use this objective formula. It equals cost equals 5x plus 10y plus 15z plus 4w. We have to express the constraints. So they tell us to make z equal 600 minus x and w equaling 400 minus y. Well, and we also have x plus z equals 600. That's for San Francisco. And Sacramento is y plus w equals 400. For the San Francisco, for Novato, x plus y has to be less than or equal to 700. And for Lodi, it has to be z plus w less than or equal to 800. Oh, it tells us to substitute z and y and express the constraint in terms of x and y. I mean, z and w for x and y. So that will give us 600 minus x plus 400 minus y, which is less than or equal to 800. Which then gives us 1000 minus x minus y, less than or equal to 800, which then give us 200 less than or equal to x plus y. Now, the total order of the books is 1,000. 800 books in Lodi, and at least 200 books will come from Novato. The implied constraints are x greater than or equal to 0, y greater than to equal to 0, z greater than or equal to 0, w greater than to equal 0. We substitute in the last two to get 600 minus x greater than or equal to 0, 400 minus y greater than or equal 0, 600 greater than or equals x, 400 greater than or equal to y. And to summarize constraints using only x and y, so that will give us x plus y less than or equal to 700, x plus y greater than or equal to 200, x less than or equal to 600, y less than or equal to 400, x greater than or equal to 0, y greater than or equal to 0. Then we graph it.
Alright, and here's our graph. These pieces of paper are pretty big.
It's a pretty good looking graph.
Thank you. But on the graph, you can see on our constraints, where we've had to mark them off.
We plot them all. We have the feasible corner points, which is 0, 400, 0, 200.
Where's 0, 200?
Where's 0, 200?
Oh, right there.
Yeah.
Sorry, the X and Y was marking it.
200, 0, 600, 0, 600, 100, and 300, 400. With this, we have to plug each and every one of them in, and because we were lazy, we did it, but we didn't write it down. But we plugged in all these for X and Y.
Because it's calculator work.
That. And we found out that the cheapest one filling in would be the San Francisco with the copies from Nevada, which costs only $4,600.
Okay, sweet. And the next problem we have, JM standing there. Give the camera to JM now.
Sweet.
All right, hold on. Let me grab my piece of paper wherever it's at. Aha.
Oh, wait. Is that it? Did you find it?
No, that's not it. Where is that?
Oh, God. Well, we are
Stop
having
that.
technical
Get out of my
difficulties.
way. Oh, fell on the floor. Of course.
Okay.
Okay, here's problem number 2. And again, we're just going to go step by step of all the possible ways you can do this to get our constraints and all that. So, here's the problem. A farmer has 10 acres to plant in wheat and rye. He has to plant at least 7 acres. There's a period there. He has to plant at least 7 acres. However, he only has $1,200 to spend, and each acre of wheat costs $200 to plant. Each acre of rye costs $100 to plant. All right, this camera's got to get out there. Can't really focus.
Okay.
Moreover, the farmer has to get the planting done in 12 hours, and it takes an hour to plant an acre of wheat and 2 hours to plant an acre of rye. If the profit is $500 per acre of wheat and $300 per acre of rye, how many acres of each should be planted to maximize profits? Okay, so we read the whole problem, and the first thing we're going to do is define our unknowns. So we're going to let X will equal the acres of wheat we have, and Y will equal the acres of rye. The second step is to express the objective function, and the objective is to maximize profit. So we need to find, of course, the most profit to be gained from planting wheat or rye. And the profit we're going to use is 500x plus 300y. And then we're going to find our constraints. And our constraints are the total number of acres has to be less than or equal to 10. Second, the farmer has to plant at least 7 acres. The farmer has only $1,200 to spend on planting. The planting has to be done in 12 hours, and those are all the constraints. So those are going to be expressed as this. Acreage is going to equal x plus y is less than or equal to 10, or x plus y is greater than or equal to 7. And the cost is going to be expressed as 200x plus 100y is less than or equal to 1200. And time has to be x plus 2y is less than or equal to 12. And the implied constraints are going to be here. They're x is greater than or equal to 0, and y is greater than or equal to 0. All right, scoot this up a little bit. All right, then we're going to our intercepts. And the intercepts show us that the feasible solutions have to be in the upper right quadrant of the graph, right? So we have our acreage and our cost, which we just had up here, and we're gonna add in our intercepts. And our intercepts for x are 10, 7, 1,200 over 200 equals 6, and 12. And those all correspond with time, cost, acreage. And y is 10, 7, 1,200 over 100 equals 12, and 12 over 2 equals 6. So what all that is, since we had to write it out, it turns out to be this graph. As soon as you can see that, might have to zoom out a little. There you go.
Yay.
Yeah, all right. So you get this graph. See, it's up in the upper right-hand quadrant, and it's gonna be split into three points here, A, B, and C, because after